So here I am on a beautiful Friday afternoon, coming to the end of this Beacon 25 conference here in Reykjavik. I'm standing with one of the keynote speakers who gave on, I think, the first day, the first full day of the conference, gave a very interesting talk on sub-Neptunes. Kevin Heng, who is at LMU in Germany, who has been studying exoplanets for how long, Kevin?
15 years.
15 years. So you were telling me just now that the sub-Neptunes are a fascinating subset of extrasolar planets, because why?
Well, sub-Neptunes are neither terrestrial planets nor gas giants, because even though they have puffy envelopes, the envelope makes up just 1% of the mass. So they have rocky molten cores, which are probably geochemically active, meaning they outgas. And so essentially nature is giving us a chance to study geology in small exoplanets. And what is really compelling, I think, is that the sample size of geologically active small exoplanets, so super-Earths and sub-Neptunes combined, probably numbers in the hundreds. So probably the sample is much larger than the sample of so-called habitable exoplanets that we know today. So we really have something to learn from this small exoplanet population.
And you think that doing the learning from this exogeology is a first step towards understanding extrasolar planets as a whole?
Well, we call it geoastronomy, so combining the geoscience with astronomy. Well, there are many things to say, but maybe the most interesting thing for this audience is that to understand science of life or biosignatures, you have to understand the false positive of biosignatures.
I'm sorry, what?
The false positives.
Okay, the false positives.
And the false positives come from geology, because rocks use the same gases that metabolism uses, methane, carbon dioxide, and so on. So this is one reason of many reasons why we should understand the geology of exoplanets.
So if we don't understand where these species, these chemical species, how these chemical species are generated by the geology abiotically, then we can have a false positive when we detect them in an atmosphere of an exoplanet.
You wouldn't be able to interpret them properly.
And we take K2-18b, you are kind of agnostic on this. It's a sub-Neptune, but since the detection of the putative detection of the dimethyl sulfide in the atmosphere, a lot of people think that was misinterpreted. Where do you stand on that?
Should I repeat the talking points of that? Well, there are really three things. One, is that spectral feature real? And then the second question is, if the spectral feature is real, is it associated with DMS? And the third is, if it's really DMS, is it associated with biochemistry? There are three questions. And none of the answers to these questions are really clear. So there are papers in the literature suggesting that it's consistent with a flat line, there's no spectral feature. There are papers suggesting that even if there was a spectral feature, there are like 90 other interpretations of it besides DMS. So I think that the jury's out. I think that's the debate.
So and you yourself think that the astrobiology community is rushing to judgment in the effort to find life. They're obsessed with the TRAPPIST-1 planet, 7 terrestrial mass planets around an M-dwarf star. M-dwarfs characteristically have a lot of trouble, a lot of problems, pose a lot of problems for any sort of terrestrial mass planet that might harbor life. But yet the astrobiology community continues to focus on these planets, and you're just saying, what? I don't want to put words in your mouth, but you're saying we need to focus on the science that we can do at hand and move on from there.
Well, I just think we are missing a step. We're going from astrophysics to astrobiology, and there's a big step in between, which is geoastronomy.
Geoastronomy.
So we should learn more about how geological and geochemical processes operate in small exoplanets in general before we are ready to answer the question of biochemistry.
And the
This is my-
fascinating thing about these sub-Neptunes, which typically are what 4 to 5 times the mass of Earth, they
4 times, yeah.
4 times. They're really neither terrestrial or gaseous. They're kind of a different animal, or did I misinterpret?
Well, most of these sub-Neptunes probably do not harbor life as we know it because the pressures, either the temperatures or the pressures or both are too high.
All right.
But this is actually an advantage, not a disadvantage. It means that if you see signs of geochemistry in these planets, you can be really sure it's due to rocks, due to geochemistry and not something else.
And they range, their radius from the star ranges from very close in, a few days in orbit around their parent stars, to much further out.
Sub-Neptunes are roughly 2 times the mass, 2 times the radius of Earth to just below 4 times the radius of Earth.
But you said there's some much closer in. They're even warm.
Yeah, they can be
sub-Neptunes.
on orbits of a few days to several tens of days.
Right. So what do we need to be doing? What does the astrobiological community need to be doing to find habitable planets that it is? That's the last question for you.
We are not there yet. There's a clear strategy in astronomy. First, find a sample of Earth analogs or Earth-sized planets in favorable conditions. So this missions like Plato will fill this gap. And then after that, take spectra of these, right? So Habitable Worlds Observatory. So we are a few decades away from that.
Unfortunately, the Habitable Worlds Observatory, the funding is in doubt.
That's
Correct?
right.
Sorry?
That's right.
Okay. Well, thank you so much,
Thank you.
Kevin. Appreciate your time.
Thank you.